Welcome to this short video where I'll show you how to use the Network Composer from the SINEC Advanced Network Suite to plan the network of a digital substation and prepare it for commissioning. I am Aylin, your virtual AI avatar, and will guide you through this video. Using the example of a fictional substation, I'll demonstrate the use of templates, what the term device type mapping means, what technologies are, and how existing Substation Configurator data can be integrated into the network planning. RSTP for redundancy purpose and PTP for time sync will be used and be calculated by the system. Finally, to prepare for commissioning, we will generate device configuration files that are tailored to the network components. To design the digital substation, I'll use a template that's already pre-configured for this purpose. You can find it in the Tech Guide section under the vertical subfolder named Digital Substation. We simply drag this into the topology. This gives us the basic building block for our substation. However, since the template only includes generic devices that specify the functional and physical requirements at different locations, but no specific devices, we need to define which exact device types will be used. To do this, we select the corresponding points. For example, for the time servers, we go to the Device Mapping area and click on Device Mapping. Here, we can see which devices can fulfill all the functions at this point. I choose one of them and assign it to the placeholder. We do the same for the central router. The system suggests a different device here, since 3 functions are required simultaneously. Next, we perform the mapping for the red boxes. Again, the system suggests the optimal devices. We continue with the process bus. Here, I can use the rectangle selection tool to select all the devices at once. Then I choose the RSTP device. Finally, we also need to map the protection devices. Just like with the merging units at the end, simply select the device, execute the mapping function, choose the appropriate device, and confirm. With that, we have created the basic structure of the substation, consisting of the layout itself and the final devices to be used. The network templates are already designed to include technologies that are well suited for this context. These technologies are represented as so-called configuration domains. In the topology, these domains can be visually highlighted by selecting the corresponding configuration domain, making it easier to see where each technology is applied. To later translate these technologies into device parameters, the next step is to create groups of devices that represent logical instances of the corresponding technology. After placing all devices, the calculation of the configuration domain instances is carried out. The calculated instances can then be individually highlighted in the topology, providing a clear overview of how the technologies are structured within the network. Since the substation's internal communication structure has already been designed in another tool called Substation Configurator, we want to reuse this information and use it to optimally align the network accordingly. To do this, we import the relevant data using an SCD file. This way, we gain all the necessary information about the IEDs themselves, how they are connected to the network, their IP connectivity, and the communication streams that will later take place within the substation. After importing the SCD file and having the system adopt the extracted information, some inconsistencies are initially displayed. This occurs because a complex calculation is still required to properly integrate the imported data into the network. To address this, the automatic mapping function is triggered. This ensures that all IEDs in the network are correctly mapped and that the necessary virtual local area instances are subsequently created. Particularly, the calculation of the paths and the associated VLANs is a highly complex process, which is presented in a simplified form in this video. This process, although intricate, saves a lot of time when incorporating the data. To take a closer look at how the system has adapted the network components, you can open the device details with a double click and view the internal structure of the devices. Now that the IEDs have been integrated into the network, it's essential to ensure that also for the management purpose, all gateways, virtual local area networks, and static routes are properly configured in order to establish full and consistent connectivity between all participants. This can be done using the Calculate Network segment action. When you select all available options, the calculation will not only create complete connectivity, but will also merge network segments that belong together and removes any empty segments that are no longer needed. This process is highly complex, so in this video it has been sped up by about 1 minute for demonstration purposes. The result is a completely consistent network where all participants can communicate with one another seamlessly and reliably. Now, we're going to design the redundancy protocol rapid spanning tree for the process bus. These networks have already been pre-configured and prepared through the corresponding config domains. Here too, individual devices are selected from the desired RSTP network. We then create a new network configuration of the type intent. Once that's done, the system can automatically generate and calculate all the necessary parameters to implement the redundancy exactly as needed. In advance, we've already determined which device will be the primary root bridge and which one will be the secondary root bridge. Likewise, we've defined which links should be blocked under normal conditions to ensure proper redundancy and a robust network design. Now, in addition to the redundancy, we're going to design the time sync protocol, PTP, for the entire network. Also for this, the network has already been pre-configured through the corresponding config domain. Again, individual devices are selected from the desired PTP domain. We then create a network configuration of the type intent. Now, the system can automatically generate and calculate all the necessary parameters to implement the time synchronization as needed. In advance, we've already determined which devices will be the master clock and which ones will be distributing and consuming the time. In the area called Version History within the main navigation Intent Enforcement, you can activate the current in-work version and apply it as the target state. This lets you continue working on network without altering the current state. To do this, simply use the Set to Active function. Now that all parameters are ready and the network is consistently designed, you can create configuration files for the network devices. In the Device Intent section, simply select the devices, click Export Config File, and the system generates them and will provide a secure download. In the Documentation section within Intent Enforcement, the software offers several types of information for download. This includes the connection diagram for each device, an overview of all assets, the complete topology, and even the so-called Station Exchange description file that allows a round-trip experience with the station configurator of the substation. That brings us to the end. I hope I was able to show you how the SINEC Advanced Network Suite can be used to design, configure, and commission a network of a digital substation. I wish you lots of fun and success in recreating these steps. Goodbye.